Welcome to Learn with us. This is the 23rd lecture of Basic Electronics.
First, we will have a quick review of our previous lecture. In your last lecture, you understood AC modeling using T model with the help of some examples. Now, what are the learning objectives of this lecture? In this lecture, you will study about configurations of transistors. In this lecture, you will also understand how transistor acts as an amplifier and what is the switching operation of transistors. Now we will understand configuration of transistors. There are three types of configuration in both N-type and P-type transistors. First is common emitter configuration. Second is common base configuration, and third is common collector configuration. First, we will talk about common emitter configuration. In common emitter configuration, emitter is connected to ground. It means our circuit diagram will look like this. Suppose we are talking about NPN transistor here, it means here arrow will be here, and if we have base resistor here, and here we have AC input supply, it is VI, which is input voltage. Here we have VCC, this is RC, and here we have output voltage, and this is emitter, which is grounded. It means here this nodal voltage will be 0. Okay, now if we have a transistor configuration like this, the arrow is here, it means it is an NPN transistor configuration, and here we have AC input supply VI, this is RB, this is BCC, this is RC, here we have output voltage, here we have VE, this is RE. It means if this RE is added in the branch of emitter, then this configuration would be common emitter configuration with D generation. As you can see here, this emitter is grounded. Okay, so this is common emitter configuration with D generation. Now we will talk about common base configuration. In common base configuration, base terminal is directly connected to ground. It means our circuit diagram will look like this. Again, we are talking about NPN transistor configuration. So this terminal is emitter and this is collector terminal. Here we have VCC, this is RC, this is RE, the arrow will be here, this is VEE, and here this base terminal is directly connected to ground. It means here this nodal voltage VB is 0. Okay, now what about input and output? Here the input supply is connected here to this emitter and the output voltage will be here. It means in case of common base configuration, emitter and collector terminals are used to take the input and output respectively. Now we will talk about common collector configuration. In common collector configuration, our circuit diagram will look like this. Again, we are talking about NPN transistor here. So the arrow will be here. This terminal is emitter. Here we have VCC, this is RE, and here we have RB, and here we have input supply Vi, and the output will be here. Okay, it means in common collector configuration, base and emitter terminals are used to give input and output respectively. Here, as you can see, this collector is not connected to ground directly, because if this collector terminal is connected to ground, then this transistor won't be having any DC supply. So in case of common collector configuration, RC is 0 and VCC has to be given to collector terminal for at least transistor to work in right mode. It means it's important to bias collector terminal, so it can't be grounded in case of common collector configuration. Okay. Now, in case of common base configuration, we prefer T model for AC modeling and finding voltage gain, but in common emitter and common collector configurations, we prefer Pi model for AC modeling and finding voltage gain. Okay. Now we will understand how transistor acts as an amplifier. Suppose you have a circuit diagram like this, where the arrow is here, it means it is an NPN transistor configuration. Here we have RB, this is RC, here we have VCC, and if we have a DC bias voltage here, which is VBB, and we have an AC voltage here, which is Vi, and this AC voltage is superimposed on this DC bias voltage VBB by capacitive coupling. It means we have a capacitor here. Okay. So this is your configuration. Now in this configuration, this AC input voltage produces an AC base current IB, which will flow in this direction. Now this AC base current will result in a much larger AC collector current, which will flow in this direction IC. Now we know that collector current is equal to base current multiplied by current gain beta. It means this AC base current, it will produce a much larger AC collector current, and the direction of this collector current is inverted, but it is amplified. Okay. When transistor is acting as an amplifier, then it is in active mode, and we know that in active mode, collector base junction is reverse biased and emitter base junction is forward biased. This forward biased emitter base junction presents a very low resistance to the AC signal, and this internal AC emitter resistance is written like this. Okay, it means it appears in series with this RB, and here we have AC base voltage here in this region, which is VB, and we have AC collector voltage here in this region, which is VC. Okay. In case of transistors, base current is very small as compared to collector current and emitter current, and we know that emitter current is equal to IB plus IC. So if this IB is very small as compared to collector current and emitter current, it means here collector current is approximately equal to emitter current. Okay. Now if we want to find AC base voltage VB, we know that from Ohm's law V is equal to IR, and as you can see here VB is here in this region. It means this VB is equal to AC emitter current multiplied by this AC emitter resistance. Okay. Now what about AC collector voltage VC? We know that AC collector voltage is here in this region, and from Ohm's law V is equal to IR. It means here this AC collector voltage is equal to the AC voltage drop across RC. So it is equal to IC RC. Okay, and we know that IC is approximately equal to IE. It means here this AC collector voltage is equal to IE RC. Okay. Now here in this case, this AC base voltage VB, it can be considered the transistor AC input voltage, and it is here. So if we want to find the equation of this AC base voltage, we will use this formula. IB is equal to VI minus VB divided by RB, because we know that IB is flowing in this region and this is higher potential and this is lower potential. And if we rearrange this equation, we get VB is equal to VI minus IB RB. Okay. We know that voltage gain is the ratio of output voltage divided by input voltage. Here this AC base voltage is considered as an AC input voltage, and here AC collector voltage is considered as an output voltage. It means here voltage gain is the ratio of VC divided by VB. Okay, and here we know that this VC is IE RC and this VB is IE RE. Okay, this IE will cancel this IE. It means here this voltage gain is equal to RC divided by RE. It means here this voltage gain is the ratio of collector resistance and AC emitter resistance. From our last slide, we know that voltage gain is equal to collector resistance divided by AC emitter resistance. It means the transistor provides amplification in the form of voltage gain, which is dependent on the values of collector resistance and AC emitter resistance. Here, the value of collector resistance is always larger than the value of AC emitter resistance, and we know that output voltage is here in this collector terminal. It means the output voltage for this configuration is greater than input voltage. Okay. Now look at this example. If you have a configuration like this and if you want to find voltage gain and output voltage, so how you're going to start your analysis? We know that voltage gain is equal to collector resistance divided by AC emitter resistance. For suppose here this AC emitter resistance is 50 ohms and we know that collector resistance is 1 kilo ohms. So if we put these values here and after solving this you will get 20. It means the voltage gain is 20. Now what about AC output voltage? We know that voltage gain is equal to output voltage divided by input voltage, and here we know that input voltage is AC base voltage, and as you can see here it is 100 millivolts, and if we rearrange this equation we get P out is equal to AV multiplied by VB. It means it is equal to 20 multiplied by 100 millivolts, and after solving this you will get 2 volts. So this is the AC output voltage here. Now for suppose if you have voltage gain 50 and if AC emitter resistance is 50 ohms, then what is the value of collector resistance? Again we use this formula. Voltage gain is equal to collector resistance divided by AC emitter resistance. It means collector resistance is equal to voltage gain multiplied by AC emitter resistance. Here voltage gain is 50 and AC emitter resistance is also 50. After solving this you will get 2.5 kilo ohms. So this is the value of RC. Now what about output voltage? In this case output voltage is equal to gain multiplied by input voltage. Here gain is 50 and input voltage is 100 millivolts. After solving this you will get 5 volts. So this is your AC output voltage in this case. Now look at this example. If collector resistance is 1200 ohms and if AC emitter resistance is 20 ohms, then what is the value of voltage gain? Here we know that voltage gain is equal to collector resistance divided by AC emitter resistance. Here we know that RC is 1200 ohms and AC emitter resistance is 20 ohms. So after solving this you will get 60. So this is your answer here. Now we will understand switching operation of transistors. Transistors act as a switch in two modes. First is cutoff mode and second is saturation mode. In cutoff mode, both emitter base junction and collector base junction, they are reverse biased, whereas in saturation mode both emitter base junction and collector base junction, they are forward biased. For switching from cutoff to saturation mode, transistor should come in active mode first. When transistor acts as a switch, it is off in cutoff mode, whereas it is on in saturation mode. Now we will understand switching operation of transistor in cutoff mode. For suppose we have a transistor configuration like this. If the arrow is here, it means this is an NPN transistor. Here we have a resistor, it is RB. Here we have VCC, this is RC, and we know that the voltage drop between this collector and emitter terminals is VCE. Now if we draw its equivalent switch, it is like this. We know that in cutoff mode, both collector base and emitter base junctions are reverse biased. So ideally, there is an open between this emitter and collector terminals. Now, we know that collector current flows in this direction. So, the formula of collector current is VCC minus VCE divided by RC, because we know that here VCC is at higher potential and VCE is at lower potential. And if we rearrange this equation, we get VCE is equal to VCC minus IC RC. Now, when this transistor is in cutoff region, we know that emitter base junction is not forward biased, and if we neglect leakage current here, it means all of the other currents are zero. That is, base current is zero, collector current is zero. Now if we put this value of collector current here in this equation A, we get VCE is equal to VCC. Okay. Again, if we talk about nodal voltage at collector VC, then the equation of collector current is VCC minus VC divided by RC, and if we rearrange this equation, we get VC is equal to VCC minus IC RC. We know that this IC is 0, it means here VC is equal to VCC. So this is the condition of transistor in cutoff mode. Now we will understand switching operation of transistor in saturation mode. If we have a transistor configuration like this, if arrow is here, it means this is an NPN transistor. Here we have RB, here we have RC, here we have VCC, and we know that voltage drop between these two terminals is VCE. Now if we draw its equivalent switch, it is like this. We know that in saturation mode, both collector base and emitter base junctions are forward biased. It means there is a short between emitter and collector ideally. Now in this case, the equation of collector current becomes IC saturated is equal to VCC minus VCE saturated divided by RC. Here the value of this saturated voltage drop between collector and emitter is very small as compared to this VCC, so it can usually be neglected. Generally, this value is 0.2 volts and it ranges from 0.1 volts to 0.3 volts. Now, what about minimum value of base current that is needed to produce saturation? We know that IC is equal to beta IB. So, minimum value of base current is equal to saturated value of collector current divided by current gain beta. It means normally base current should be greater than this value to ensure that the transistor is saturated. Now look at this example. If you have a transistor configuration like this, where you have a resistor here, this is RB, here you have input voltage, here you have output voltage, here you have VCC for suppose it is of 10 volts, and here you have RC and for suppose it is of 1 kilo ohms. Okay, now if input voltage is 0 volts, then what is the value of VCE here? Okay, when the value of input supply is less than 0.5 volts, then the transistor is in cutoff mode. It means here this transistor is in cutoff mode, and we know that in cutoff mode VCE is equal to VCC. It means here VCE is also 10 volts. Okay, so this is your answer here. Now for the same transistor circuit, if you want to find the minimum value of base current that is needed to saturate this transistor, if beta is 200, and for suppose here you neglect saturated value of this voltage drop, so how you are going to find this minimum value of base current? First we will find saturated value of collector current. We know that IC saturated is equal to VCC minus VCE saturated divided by RC, and if we are neglecting this term here, then here IC saturated is equal to VCC divided by RC. Here we know that VCC is 10 volts and RC is 1 kilo ohms. It means here this saturated collector current is 10 milliamperes, and we know that the formula of minimum value of base current is equal to saturated value of collector current divided by beta. It means here we have 10 milliamperes divided by 200. After solving this, you will get 50 microamperes. This is the minimum value of base current. It means this value is necessary to drive the transistor to the point of saturation. Any further increase in this value of base current will ensure that the transistor remains in saturation mode, but there cannot be any further increase in IC or collector current. Okay, so this is your answer here. Now for the same transistor circuit, how you are going to find the maximum value of this RB? It means how you will find RB max here when Vin is volts. Okay, so when the transistor is on, it means here this input voltage is greater than 0.5 volt. It means here transistor is on. Okay, it means here this base emitter junction is forward biased, and we know that when this base emitter junction is forward biased, then it has a constant value of 0.7 volts. Okay, now we know that here we have 5 volts and here voltage is 0.7 volts. It means the voltage drop across this resistor RB is VRB, which is equal to Vin minus VBE. Here this Vin is 5 volts and VBE is 0.7 volts. So after solving this, you will get 4.3 volts. This is VRB. Okay. From Ohm's law, we know that V is equal to IR. It means R is equal to V divided by I. Here R is RB max and this V is VRB. In our previous slide, we have calculated IB minimum. So after putting these values here, we know that this is 4.3 volts and the minimum value of base current was found to be 50 microamperes. After solving this, you will get 86 kilo ohm. So this is the maximum value of RB that is needed to allow a minimum value of this base current. Okay, so this is your answer here. Now if you want to find minimum value of base current that is needed to saturate the transistor, if beta is 125 and saturated value of VCE is 0.2 volts. Okay, again first we will find saturated value of collector current. We know that it is equal to VCC minus VCE saturated divided by RC. If VCC is 10 volts and if RC is 1 kilo ohms, then if we put these values here, we get 10 minus 0.2 divided by 1 kilo ohm, and after solving this you will get 0.8 milliamperes. This is the saturated value of collector current. We know that the formula of minimum value of base current is saturated value of collector current divided by beta. Here we know that this value is 0.8 milliamperes and beta is 125. After solving this, you will get 6.4 microamperes. Okay, so this is the minimum value of base current which is necessary to drive the transistor to the point of saturation. Okay, any further increase in base current will ensure that the transistor remains in saturation mode, but there will be no further increase in collector current. Okay, so this is your answer here. That's all for today. Now, what are the key takeaways of this lecture? In this lecture, you studied about configurations of transistors. You studied that there are three types of transistor configurations. First is common emitter configuration, second is common base configuration, and third is common collector configuration. In this lecture, you also understood how transistor acts as an amplifier. You studied that transistor acts as an amplifier in active mode. Here, you also understood switching operation of transistors. You studied that transistor acts as a switch in two modes. First is cutoff mode and second is saturation mode. You studied that in cutoff mode, transistor acts as an open switch, whereas in saturation mode, transistor acts as a closed switch.
Thank you for watching this video. If you have any questions, then write your questions in comment section of this video. Don't forget to subscribe our channel and share it with your friends and family. Thank you.